the training data will become more interesting. On the robotics project, the same thing has occurred as well with the space of perturbations that we asked the neural network to be robust to. That as the neural network was becoming more competent, we asked it to solve more challenging perturbations. And I think that these kinds of ideas of automated curriculum will be very important in the future.
Are there domains beyond the ones you already looked at, or within other aspects, special cases of the domains you looked at, do you see self-play being, or the more general form of self-play being successful in the future?
So I think that self-play is a little bit narrow, but the idea of automated curriculum is extremely broad, and it will be applicable to many situations. And I think it's quite likely that in the future, instead of having just shoving a data set blindly into a system, we will have systems that will use their own intelligence, their own understanding of the data so far, to decide what data they want to consume next. And it will lead to very large, at the very least, very large efficiency gains, but possibly even more than that. It may lead to qualitative gains.
One of the cool things you said is with OpenAI 5, I think with OpenAI 5 beating Dota, if not the greatest, it's one of the coolest accomplishments of the last year. You said you might have arrived at a strategy that's impossible to exploit. Beautifully put. But is there other insights, lessons, cool things that you've learned about reinforcement learning from taking on that huge challenge?
Definitely. The Dota project taught us a lot about large-scale reinforcement learning. And one of the big lessons from the Dota project is that large-scale reinforcement learning is not a black box. If you look at the Dota result, from the outside it may look like it's just large-scale reinforcement learning. But I think reality is more subtle. The thing that we really learned from the Dota project is that it is the combination of large-scale reinforcement learning with a gradually increasing automated curriculum, which is partly manually guided. In other words, the large-scale reinforcement learning creates the equivalent of a very eager, very motivated student that really wants to do something good but may not know how. So sometimes such a student will get stuck. And that's where you, the mentor, need to step in and guide it a little bit to get it unstuck. And so this kind of gradual, incremental process of learning, I think, is very interesting, and I think this will be another feature of future systems. It won't be a monolith. There will be real stages to learning.
What do you think next steps are? What do you think the next breakthroughs here will be, and for OpenAI 5 for you, that you've been thinking about?
Well, I mean, at this point, the Dota project has achieved its objective. And I think the future of reinforcement learning lies elsewhere. I think that basically my thinking, the way I'd put it, so far, the humble tools of deep learning have exceeded all our expectations. And right now we have unbelievable demos, in my opinion, in lots of different domains. So I think it's time to be more ambitious and to really try to solve problems that will move the needle, that will make a difference. And I think that with reinforcement learning specifically, I can easily see, I think that domains like personal assistants and dialogue agents and also self-driving cars are all areas that will benefit from reinforcement learning. And for OpenAI specifically, I think there is still, we have some ideas of using reinforcement learning, and once we have results, we'll be happy to talk about them.
I can see you trying not to reveal any of the exciting stuff that you're working on currently. Okay, let's jump to another super interesting topic that you already mentioned in your talk, but you didn't get into too many details, which is GPT-2, language modeling, generative modeling. First of all, what is it and how does it work? What's the fundamental mechanism behind GPT-2?
So, GPT-2 is a large neural network that was trained to predict the next word in text. That's it. Because the neural network is large, and because it was trained on a lot of data, it ended up learning to perform this task quite well. And as I mentioned earlier, there is a good argument to be made that if you predict the next word well, you must understand something real about language. The better you predict the next word, the more you understand.
On a scale of 1 to 10, how amazing is that? Because I'll put that like at an 8. It's incredible that by training in a self-supervised way to model the next word, you're able to learn so much about fundamentals of language.
I agree with that. And I'll make a digression here as well. This fact and facts like it are the reason why there's been an unsupervised learning revolution behind the scene. Unsupervised learning in general went from basically being a long-term intractable dream of machine learning to something that's routinely used all the time by the best systems. And GPT-2 is one example of them. And the principle of predicting the next word is one of several such unsupervised learning principles.
Is there something especially interesting about transformers and the ideas behind language model success that you want to comment about?
Yes, well, transformers are interesting because they work so well.
What are they, first of all? What's a transformer?
It's a certain kind of neural network architecture that has a number of simultaneous good properties, whose combination makes them work far better than all previously existing network architectures. And they work really well on tasks like language, where you want to model long sequences, where you want to predict the next token in a long sequence. And it doesn't have to be language, you can apply them to other modalities as well. And so you take this big neural net, you apply it to lots of data, and you get a neural net which can predict the next word quite well.
So in slightly different context, can you describe what is MuseNet and how it's connected to this world that GPT-2 unlocked?
Yes, so because once we saw that the transformer can predict the next word well, it became clear that it should be able to predict other things well too. For example, the next MIDI note. And if you do that, it could generate very, very nice sound music, which, if you're curious, I should suggest you check it online. It's genuinely fun to listen to. It's interesting to see that a smooth, continuous, approximate neural network is able to learn many of the rules that music needs to obey. Music obeys symbolic rules. Music is not structureless. Some music is structureless, but most of it isn't. Classical music definitely isn't. And yet, by simply learning to predict the next note, the transformer, MuseNet, learned the structure and was able to respect it.
As a musician, that's very exciting. Or terrifying. What's the future of this line of work of predicting the next thing in language models, and more generally? What do you think, where are the applications? You kind of said that it's time, and I would say GPT-2 is already taking a step from the demo to real world. But what do you see as the next steps of having a big impact or solving fundamental problems in learning?
Yeah, so I'd say several obvious trends will continue. Unsupervised learning in general will become a very indispensable tool of all machine learning practitioners, just like supervised learning used to be that tool for the last N years. Another thing that we'll see is that these models, these generative tools, will lead to lots of exciting generative applications in terms of generating art, generating music, text, helping with creative writing, helping improving writing, conversational agents. I think all this class of applications will flourish because of the advancements that have been made in large-scale generative models.
So you've been behind some of the biggest ideas in machine learning in the last few years. Like we said, from the AlexNet and ImageNet to sequence-to-sequence, from language modeling to reinforcement learning. Can you maybe take a step on sort of a personal process note and the great collaborators you work with? How do you think about ideas? How do you generate new ideas? How do you think about the space of neural networks when you search for new breakthrough concepts of how we can improve ideas in this space?
Well, the honest answer is that I try really hard. But beyond that, I mean...
What does trying really hard look like?
Well, I mean, it helps if you care a lot about this stuff. It helps if you find this stuff very interesting and philosophically fascinating. I think it's very... Like, when I was studying computer science for the first time, it looked like there is just no way that these dumb rule-following machines could ever be intelligent or could ever learn. So I found it exciting that you could have even the smallest demonstration that a computer could learn. And that also this little demonstration is inspired by the brain. How amazing is that? So machine learning has this very satisfying multidisciplinary component to it. You have cognitive science, you have neuroscience. Now, of course, not very deep cognitive science, not very deep neuroscience, but you've got a little bit of that. You've got a little bit of almost, I would say, philosophy where you reason about how learning should be, so maybe psychology. And of course, you've got the full stack of from low-level GPU programming to distributed systems. So machine learning is not a narrow discipline, it's actually a very broad discipline. And I like it for that reason. And so that makes it fun to work in AI. And of course, it's also very impactful.
What would you say is your favorite or maybe the most beautiful, surprising idea that you yourself have developed or others have developed in the, I guess, last decade in deep learning?
So I think my favorite idea is that deep learning works in the sense that if you train a large neural network on a lot of supervised data and with a lot of compute, then you will in fact succeed. And this has been shown again and again. This is the fundamental power of deep learning. It's also now been shown for reinforcement learning as well, where if you've got your large neural network, lots of experience, and you're optimizing your reinforcement learning cost function, you will succeed as well. So it just seems that deep learning really is like, it's like an asteroid. It's like the asteroid of deep learning, moving. It's like an unstoppable force. That's how it feels to me almost. And I find that to be very fun, fascinating, satisfying.
When did you first realize, okay, so the fact that deep learning works at all is amazing. When was the moment you first realized, whoa, this actually works?
Well, it's not a single moment, because I would say, okay, the answer to your question is that this realization is a continuous realization. In fact, we, the machine learning community, we realize this each year when our tools do something impossible yet again. Like, for example, in the early days, in 2012, 2013, things worked quite well on vision. Nowhere near as well as they work today. Things were just starting to work in language. Things didn't work in reinforcement learning. And since then, our capabilities have expanded, and now we work well in all these domains. There are still things we cannot do. Our models are not robust. They still make very silly mistakes. They cannot reason. And who knows how long these things will take. But I wouldn't underestimate the power of simple deep learning. I think it surprised us a lot. So the real answer is, whether something works or not, it's a moving target. But things have definitely exceeded expectations.
So if deep learning is an asteroid, there's very few people that ride that asteroid better than Ilya. He's one of the greatest computer scientists of our time. Is somebody I really look up to. He clearly wastes not a single word in describing the concepts. One of the greatest educators of ideas. So please give Ilya a big hand.